So for the time part of the equation, we end up with basically the same solution because we have basically the same equation. So d squared t of t dt squared plus beta squared v squared t of t equals 0. And the only difference here is that we have this extra factor of v squared. And so what we'll get is that the solution, going through all the same steps, we could go through all the same steps, we end up with some constant d cosine beta v times t plus e sine beta v times t. Recall that we know what beta is. We already solved for that. Beta is equal to n pi over L. So we can plug that in, and what we'll do is we'll call this beta times v, this n pi v over L. We'll give it this term omega n, just to simplify it so we don't have to write it over and over again. So t of t is equal to d cosine omega n t plus e sine omega n t, where this omega is defined according to this equation here. Now, unlike the x part, the t part has no boundary conditions. So the only boundary conditions we had were for the x part of the equation. And so we're done. We don't have to satisfy any boundary conditions. So we have figured out the entire ux of t is just x of x times t of t, and we know what those are. So we have our b sine n pi x over L. That's our x of x, and our t of t is what we have above. So this is d cosine omega n t plus e sine omega n t. Now what we can do is we can sort of combine this beta, or this b, sorry, rather, into these constants over here, so that we don't have a constant term on our x part. And so we can rewrite this as f cosine omega n t plus g sine omega n t times sine n pi x over L. And again, n here, 1, 2, 3, is a set of integers. And so this is a whole set of solutions where we have different values of n. Now the general solution is we can take any linear combination of these sets of solutions. And so the most general way to solve this is that u of x of t is equal to some sum starting at n equals 1 up to possibly infinity of a set of constants fn cosine omega n t plus gn sine omega n t times sine n pi x over L. So we can take any combination of these different n values and add them together with different weighting factors, right? So this f and g, these are, you know, sort of how much of each of those do you add in to these waves that we're creating. And so each value of n is what's known as a normal mode of the string. So it's the string vibrating at sort of a natural frequency for the string. And so another way to write this that is still equivalent but is slightly more convenient, and what we'll use when we actually use these equations, is that u of x of t, we'll write it in terms of just one of these functions for the t part with a phase shift to kind of shift things around, is a sum over all these different n values of an cosine omega n t plus our phase shift phi n sine n pi x over L. We won't show going between this form and the previous, but they are mathematically equivalent to each other. So AN here is the amplitude of mode N. Phi N is the phase. And omega N, just as a reminder, is N pi V over L. And so the next video, we'll take a look at what do these solutions look like and how do they change with time. I think this is kind of the most fun part of this, is looking at, what are these, we got this math, but what does it actually tell us about a vibrating string?